And
No.
and we have to enter it up there almost backwards.
Okay, so we're going to continue our discussion from yesterday that was woefully short. Okay. Okay, so we're going to go to dual display because it just works a little better with what I'm going to do here. So the range T, this is an example, is a set.
This is more fun.
Yeah.
I find it difficult to read.
Yeah, can we go to the front? Okay.
You guys need directions?
Yes. Yes.
We're worried about making this bigger.
And if you like tilt your glasses like at a vertical angle a little bit, like if you know that like this, like this, it says like -7. Yeah, does that help? A little. Okay.
That always helps. Pulling your eyes a little bit. That always increases scope.
Oh, never tried that before.
Yeah.
Really?
Michael.
Oh, it does. It really does. If you've ever needed glasses, that's a trick that works.
That's not socially acceptable.
I mean, I'm fine.
That means you have good vision. I mean, it essentially makes you a little less.
But this is good fun. Do you wear contacts?
Yeah. Perfect vision.
I did. I do now, but I had LASIK and I was really good for like 12 years and then it just goes bad. Okay, so yeah, this doesn't look great. Who's having difficulty seeing?
I mean, I'll be able to see it. It's just like a headache will develop.
Well, this is just for these. It's just for these two slides. I'll make the matrices a little bigger. Right. Here's matrix A. Here's matrix U. And here is matrix C. Was I supposed to hide that B? That's I love it.
What does that look like? Really weird.
I don't know. B is 7, -5, 9. Sure. Let's go with that. And C is 5, 6, 2. We'll go back off dual page in a moment. So we're going to define the matrix transformation. Now this transforms a matrix from R2 to R3. You'll note that it goes from a vector x1, x2. You can't have soda in here, George.
George.
You ever brought soda to class?
Yeah.
And you have drunk it open?
Yeah.
What do I do with my life? All you can have is water. That is
But what if it's cold
You
water?
let it general
Water.
rule, it's like,
Yeah, but this won't stain.
that's what I thought. But like, some teachers enforce it more strictly than others. Really?
I can get the handbook. If you don't finish this, you're still getting homework there. No. So you'll notice that we start off with a two-dimensional vector, x1, x2, and then we end up with a three-dimensional vector, and you get that by matrix multiplication. So what we discussed was that you could achieve a transformation through matrix multiplication, and we transformed a matrix from being a two-dimensional matrix to being a three-dimensional matrix. And if you multiply A times X, you get a X right here, which is a three-dimensional matrix. So the first thing that this asks is find TU, which is the image of U under the transformation T. So TU is achieved by multiplying A times U. Because T is defined by multiplying A times X. So A is 4, 1, negative 1, 3, 2, negative 5, and U is 4, negative 1. And when we do that matrix multiplication, we're going to do 4 times 4 is 16, plus negative 1 is 15, negative 4 plus negative 3, and 8 plus 5. And now I have transformed the matrix. Any questions on that? So then part B, find an image X, find an X whose image under the transformation T is B. In other words, I want you to find what the pre-image is if the image is B.
What's the pre-image? That's the U value?
What's that?
The pre-image, is that the U value?
It's the original, but it's the X.
Yeah, you can look at it either way.
So it's, oh, the X value, but it's the U value in this case, the 4, 3, 1.
Yeah, so you can look at it this way. 4, 1, negative 1, 3, 2, negative 5 times x1, x2 would have to equal B, which is 7, negative 5, 9. So you have a couple choices there. If you can either set up an augmented matrix and do elementary row operations, or we have actually more information than we need to solve this system. We can just say, I'm going to go over here for this one, 4x1 plus x2 would equal 7. Negative 1, x1 plus 3, x2 would equal negative 5. Already we have a system of 2 equations and 2 unknowns, so we could solve it as is, and then just make sure it works for row 3. If it doesn't work for row 3, what does that tell us? Yeah, and if it is an inconsistent system, what do you know about B? And then B would not be in the what?
In that, no, in the range.
In the range. It's in the codomain because it is in R3. So R3 is the codomain.
The range.
The range are all values that are actually reached in that codomain. So if you can't reach that codomain through adding weights on, real numbers onto x1 and x2, then it's not in the codomain. Did anyone solve and find x1 and x2? Margo?
I got x1 equals 2, x2 equals -1.
Perfect.
I just wanted to.
Thanks, bud.
You're welcome.
I looked here.
I think it was approval on complimenting.
Okay. So there is x, the vector that is the pre-image for B. Is there, oh, go ahead, Ray. You were answering C. Oh, sorry. I thought you were saying that, no, there was not more than one X. But maybe you were just doing that in a short dream of mine that I had inside. Go ahead, Jeffrey.
Can you re-explain the inconsistency you said? Because I kind of missed it.
Okay, So if you solve this system and you get 2, -1, and let's say 2, -1 doesn't work in the bottom equation. So 2 times 2 plus -1 times 5 doesn't equal 9. So it doesn't work in the bottom equation. If that was true, that means that you have an inconsistent system, and that means that you cannot reach, as long as you didn't make an error there somewhere, you cannot reach that vector with these two vectors, a linear combination of these vectors.
Okay.
Meaning this is not in the range of those two vectors. It's not a linear combination. Is there any other pre-image of X, or is this the only one? Right?
Would it be the only one because you solved for it? If there were more, you'd be able to even like figure it out.
Yeah.
Correct. So if we did elementary row operations, or let's say this system here, because I know I didn't do elementary row operations because I just kind of felt like we were in algebra 1 land here. But if we ended up with an infinite number of solutions here, where we could define a line in which this were true, that meant that we would have an infinity of solutions that would provide this particular vector. So that's why it would be, it could be a yes, but it's a no, because the only answer we got was 2 to -1. Now, is C in the range? In other words, could I get C through doing the same thing?
Probably not.
So in other words, to find that, and I can use elementary row operations for this if I want, just to kind of switch over to algebra, linear algebra land, and use an augmented matrix, just so we can show more than one way to skin the cat.
Was that first example that we did? Like getting X on an X2, would we then have to like plug it back in for X, like the third equation to ensure that like that third value isn't off?
You would, or else you're not making sure the Z's line up.
So in this case, like we're doing it because it's elementary row operations, we're gonna have all three and it'll show us, but otherwise we have to plug it back in.
Yeah, because here I didn't really take into account the third row, so I had to make sure it worked for my third row in the method I used for part B. But now for part D, I'm just going to check to see if C is in the range. In other words, is this a consistent system? So I'm going to do 2R1, I'm sorry, 2R2 plus R3. So I get 0, 1, and then that would be 14. And then I'll do R1 plus 4, R2.
Yeah, that's just not gonna work.
All 13. And then,
Dude, why do you need to do a second elementary row operation? Don't you already have what X3 equals? Or yeah, sorry, X2 equals, and then can you just go through?
oh, sure. Yeah, I suppose. I'm just seeing if any of my rows go nuts.
Uh-huh.
Because if I end up with 0, 0, non-zero, I know it's an inconsistent system.
Yeah.
So it just keeps me in matrix land for a little longer. 4R2, sorry, 4R2 would be 24, 29.
Which there again would show that X3 or X2 doesn't equal the same thing.
Yeah, so if you guys see this, my X2s, when I subtract these rows, yeah, I'm gonna get 4, 1, 5, and then if I scale this, I'm gonna get 0, 1, 14, and 0, 1, 29 thirteenths. And then, when you subtract, do you see how you're gonna get a row that has 0, 0, non-zero? Okay, so that's the matrix way of me saying this is going to be an inconsistent system. So therefore, no. Because you'll have 0, 0, non-zero quantity. Or you could have gone out of the matrix, solved for R2, and then these two, R2 would have been 14 and R2 would have been 29 thirteenths. Questions on that? We'll go back full screen.
Who knew there were so many functions to this smart board? Oh no.
Okay, so what we talked about yesterday when we kicked off the lesson was how you can achieve geometric transformations using matrix multiplication. And one of those matrix, or one of those transformations is called a shear. So taking a geometric shape, and really you can take that shape in any 2 or 3 dimensions, and to shear something means 2 of the sides, essentially, one of the sides remains unchanged in its location. The other side is moved or translated in a way that is parallel to the other side. So this would be considered a horizontal shear because you move the top side horizontally, therefore creating a parallelogram where you used to have, or it's always a parallelogram, but you created a non-rectangular parallelogram. So what we have done is sheared this rectangle. Is area preserved when you shear?
Yeah.
Yes.
Yeah, and you can kind of even see it in a picture
Yeah.
because you lose this area here, but the same area is gained over here. So area is preserved during shear. Area won't always be preserved during these geometric transformations, but this is an example of one that is.
Did it say like physics applications or like earthquake applications or something?
It has.
Okay. I was just curious if like it was in the textbook or something.
No. Well, like we've done shear forces, yes. I'm talking about like earthquakes more specifically. I don't know, whatever, it doesn't matter.
So accomplishing shearing is, and we're going to focus on 2 dimensions at this point, as I said, can be done by multiplying by a matrix. And we're gonna be multiplying by a 2x2 matrix because we're not trying to take our vectors out of the 2D plane. We're just trying to transform it. So if you take a point in 2 dimensions and you multiply it by the shearing matrix, 1m, 0, 1, it will accomplish a horizontal shear. So xy is a vector, and then x prime, y prime is the sheared vector. So this is the image and this is the pre-image right here. And down below, we have an example of vertical shear if a couple of the points would be moved vertically. And you can see that the m value goes from its location in the upper right to the lower left. And that then changes the y value of the vector instead of changing the x value of the vector, yielding a vertical shear versus a horizontal shear. So we're actually going to look at what that does to a shape in 2 dimensions. They're just using that instead of the brackets. Okay, so let's take the square and let's shear. So the square, you can shear these position vectors individually, or you can shear them all at once. So the square is defined by 4 different position vectors because it has 4 different vertices. Yes?
Is it supposed to be a square, like that?
Oh no, it's supposed to be a rectangle. Because I wanted it to be rectangular.
Why does it matter?
It's just better
It's like
if it has less,
specificity.
like symmetrical properties, just so you can see more changes. Yeah. Rectangle, thank you. So let's define the rectangle by its vertices. And again, you can do this all at once, or you can do it as one big shape. So we're going to first do a vertical shear, or do you guys want to do them all individually first? And yeah, let's do them all. What time? What do I have?
255.
Yeah, a lot. Okay, we're going to do them all together. So we're going to shear it vertically. So that's A. And normally I would just multiply A times X to do the transformation. But I'm going to multiply A times, yes.
How do you get A?
So A is defined as this for vertical and this for horizontal. And so I'm just choosing 2, so everything is sheared by a factor of 2. So those are doubled. Yeah. So I just, as a next number to use. So here's my vertical. And you can multiply by all of these vectors separately, or all these position vectors separately, or all together. So I'm just going to do them all together. So one vertex is 0, 0. Another one is 3, 0.
Oh, that's so cool.
Another one is 3, 4,
What's the right?
and then 0, 4.
Okay.
So we're gonna call this X, even though it's 4 vectors. So like X1, X2, X3, X4. So you guys go ahead, do your matrix multiplication, and tell me what my new matrix would be.
Oh, that's so cool.
Did anyone else get that
0, 4.
Yeah, 0, 4.
for the last one?
Isn't it row by column?
It's 1 times 0, 0 times 4.
Yeah, okay. Okay, so let's graph the shear.
Why is the last one 4 and not 10?
2 times 0 plus 1 times 4.
Never mind. Thanks, Ray. I'm just a little slower, okay? Don't try to do it, just happens.
So this, that's a vertical shear. So one side just moved. Did I mess up?
No, just
The left top one isn't supposed to bring the same stuff.
No, bro, you get that.
No, it's a vertical shear.
that's the.
Oh
yeah, sure.
The left
Yeah,
top.
yeah, that's-
Yeah, you already tried.
The left one.
Oh, the next one?
Yeah.
One, Homer, one, I drew that line so I can.
Why do you just have to run everything?
How is this?
Like, this is literally why we can't have this.
Because that.
Okay, so there is our vertical shear. We took one side, moved it vertically, so it's essentially up, double. Okay, instead of, or, well, more than, it's a combination of being up by the x and the y, so that's why it's up to 10 here on the y. So, yes.
I'm just curious, how did the factor of 2 translate into a vertical shear of 6?
Or the factor of 2.
Like 102 1 becomes 6 in turn.
Because you're multiplying the 3 by 2 and adding it to the 4.
Well, okay, I get that. It's like mx plus y. So this is going to be for 3, whatever the 3 would be by one portion. So if it was like 0, 4, 4, 0, it would end up with 8 as well. Okay.
Michael?
What would you do if you wanted to like share the other side? The side
every X side going the same stuff.
How would you shear this side?
What do you think you would do?
So what matrix would you multiply by, Michael?
0, 1.
0, 1, 1, 2. So you could try that.
And it won't work, is what you're saying?
We have to think about what making this 0, 1 will do. We're going to learn more about how to create these matrices. That's part of the evolution of this. But this does something.
Bad.
Does something. Yes. 2, I just randomly assigned a value to shear it by. A m can be any number.
Is it bad?
Yes.
If you did a 1, would you get the same thing, you guys? What do you think?
You do what?
If you had a 1 instead of a 2 here, would you get the same thing?
As your
By bringing stuff, so it's like, you get 3, you get 3 instead of 1. You get 3 instead of 1.
Okay. So, Ben, what did you say?
Well, so having the 1 in the bottom left corner is like saying x plus y in there. So what you would want is a 1, 0, 0, 1, so that you have y and x as individual variables.
Which is called the what, Jeffrey?
Yeah.
Yeah, so what keeps it the same is 1, 0, 0, 1, which is your matrix identity. But the 1 is x plus y. It just lowers your shear. It's just not as high.
Wait, to Michael's question though, like,
So you could do it, you would have to figure it out.
how?
So you'd have to figure out how to shear this instead of that.
Wait, isn't what Michael said, wouldn't that work or no?
Well, let's try it.
Maybe 1, 1, or 1, 2, 0.
This is 0, 0, so
Yeah, I don't think it's
1,
possible to shift the 0,
1,
0.
2, did you say?
Yeah, 0, 0 vector wouldn't shift, but the other end should shift,
Isn't
because
that inverted?
the 0, 4 would shift, right? Because you get a 0, 1,
We could try this.
You get 8, man, I just can't speak.
This is 0, 0.
It's gonna be real nice and fast. 0, 8, right? Oh no, never mind.
Oh, sure.
Wait, it'll just be 4. It'll just be a 4 and an 8. It's still the same thing. No, it should be the same height as the other one, or the same.
The other one's also 4.
Yeah.
10 and the 3.
It should be over 1. So interestingly, it looks like the area stayed the same. What, Margo? You just knew that ahead of time? Well, I mean, we kind of built the form of what we had been doing, so that's right.
Close.
Like,
Your work should have done something completely different.
So Michael wants the left side to go up.
So we failed
or to
this.
move away from the x.
So you want to reflect it.
if you have a column and the x at 0, 0, when you like always end up with 0.
For that point. So there's always going to be a point.
So how is it possible?
You have to add 2 matrices
Well,
together.
can you have a 0, 0 and still do this?
Well, you're sharing it up.
Okay?
That means last time.
So we're gonna learn how to, so did you hear what he came to? We're kind of anchored to 0, 0 with these multiplications. It seems. But we're gonna learn how to translate these eventually. So we need to keep going. Okay, so we need to define these transformations as whether they are linear or not. So a linear transformation is defined if they are the following. The first is called closed under addition. And let me describe to you what this means. The equation is just in math what it means. In words, what it means is if you take the transformation of the sum of two vectors, it's going to turn out the same if you transform one vector and add it to the transformation of the other vector. So in other words, you can transform a sum of two vectors, or you can transform a vector, transform another vector, add them, you'll still get the same thing. So the vector addition is essentially commutative with transformation. You can do it in either order. Also, scalar multiplication is closed under the operation of the transformation. So if you take a vector and you scale it, and then you do the transformation, versus if you do the transformation and then you scale it, it's still going to be in the domain of T, and it's still going to be equal. Okay? So it doesn't matter whether you scale first and then transform, or you transform and then scale. These all have to do with the order in which you operate. So that's what it means to be linear. Remember when we talked about linear combinations? Linear combinations mean we could add any multiple of any sum, and could we create a vector with a multiple, a sum of multiples. So here's the sum, here are the multiples. So this is the connection to linear. So linear transformations preserve the operations of vector addition and scalar multiplication. So this is bringing all of these together. This is kind of like the distributive property of you distributing the transformation over the sum of two vectors that have been multiplied by scalar quantities C and D. So if you have two vectors that are in the domain that you have scaled by a factor of C and D, you added them, and then you apply the transformation, that's the same thing as if you transform them first, multiply them by the scalar, and then add them. So you can do all of these properties before, during, or after, and you still get the same thing in terms of scalar multiplication and addition. That's what makes them linear transformations.
Quick thing.
Okay, so we're going to go through this a little quickly because I do know the time. This is something Michael discovered through his question. Was if you transform the zero vector, you get the zero vector if it is in fact a linear transformation. That's why we couldn't move the origin, which tells you that when we translate, it's not a linear transformation. Yay, read that later. We don't have time for that. This just means you could continue to add a whole bunch and it still stays true. And then, yes, that's a really easy problem. And then here,
We made it.
and so when Ben asks, are we gonna do 1.5 lessons soon? Barely do.
I really thought it was good fun. Were you there? Remember when I lasered?
So you didn't get into this.
One more time.